Tonight, we're exploring one of the universe's most soothing mysteries: why everything, from planets and stars to tiny drops of water, becomes round. We'll uncover how gravity acts like a patient sculptor, shaping chaos into calm, smoothing sharp edges into curves, and teaching us why the cosmos prefers circles over corners. We'll journey from the birth of worlds to the hearts of stars, to the invisible pull that even light cannot escape, all to understand why roundness is nature's favorite design. If these peaceful journeys help you unwind, I'd love for you to subscribe and join us again. And now, take a deep breath. Let your thoughts soften. Let the universe spin gently around you, calm, endless, and quietly alive. Take a moment and imagine holding a handful of sand. Let it sift through your fingers. The grains don't leap away in random directions. They fall, slowly converging, finding the bottom of whatever container is there to catch them. That's gravity's handwriting. It's patient, almost indifferent, but relentless. You can't hear it. You can't see it like a gust of wind. Yet everywhere you feel the result, how things settle, how they stack, how they eventually make room for one another. In the vastness of space, where there's nothing to slow it down, gravity gets to paint without interruption. On the grandest scales, every particle tugs on every other one, not in sudden jerks, but in a continuous, mutual pull. Think of each particle as offering a tiny invitation to every other particle. Come closer. Over billions of years, those invitations add up. A diffuse cloud of gas that starts more like a messy soup will, imperceptibly, begin to gather at the center. The motion of individual atoms turns into an overall flow inward. Kinetic energy and angular momentum rearrange into shape and structure. What begins as chaos becomes a form. Why a sphere? It's elegant because it's simple. A sphere is the only shape where, for any point on the surface, the pull inward is the same. If something is free to move and each part feels the same tug from every direction, the most stable arrangement is one where nothing sticks out to catch more pull from one side than another. Corners and edges are inefficiencies. They offer a direction for the pull to be stronger, so matter slides, flows, or collapses until evenness is restored. In an environment where friction and rigid supports are almost non-existent, space, the result is almost inevitably round. Bring this down a notch from astronomical distances to something closer to home. Have you ever let a drop of water fall into a still pond? At the instant it's separate, surface tension and a variety of forces give it a shape. But in microgravity, floating drops are spheres. I remember watching footage of astronauts aboard the International Space Station, where a bead of water hangs, perfectly round, like a tiny planet. That simple image captures the same principle at play. When the influences around a body are uniform, and there is nothing to hold it in any other configuration, symmetry wins. Gas clouds are particularly good storytellers of this process because they start so unconstrained. Imagine a huge, cold cloud of hydrogen and helium spread thinly across light years. Inside, slight variations in density, maybe a little bit more gas here, a touch less there, make tiny differences in gravitational attraction. The slightly denser regions pull in neighboring gas, becoming denser still, and the cycle feeds itself. It's a slow snowball effect on a cosmic timescale. Where you and I might think collapse, the cloud experiences a gentle, progressive focusing of mass toward centers. Over millions of years, clumps form, spin up, heat up, and if they get heavy enough, pressure in the core ignites nuclear fusion. A star is born. Planets follow a similar script, though their formation is more intimate, involving collisions, stickiness, and a process called accretion. Dust grains in a young star's disk collide and cling. Then those clumps collide with other clumps, growing into pebbles, boulders, protoplanets. Gravity takes over, smoothing irregularities. Early irregular shapes that might resemble lumpy potatoes slowly give in, their higher points pulled down, their valleys filled until the body's self-gravity is dominant enough to erase most of the bumps. The final shape is a compromise between gravity's preference for a sphere and the object's ability to resist deformation. Its rigidity and rotation can introduce slight flattening at the poles, but the overall tendency is toward that quiet roundness. There's a poetic side to this physics. Gravity doesn't carve monuments. It organizes. It's not violent in the cinematic sense. It doesn't shout. It whispers, nudges, and over eons convinces molecules to cooperate. In that whispering, it chooses balance. Imagine a room where everyone wants to stand as far from everyone else as possible while staying inside. After a while, they'll arrange themselves evenly. Gravity is the opposite. It wants closeness, but in such a way that the closeness is the same in every direction. The result is harmony rather than chaos. That harmony shows elsewhere too. Stars, once formed, often shape their immediate surroundings through winds and radiation, but the underlying gravitational hand remains the sculptor of deeper structure. Galaxies, for example, spin and stretch and collide, yet even they settle into organized forms, spiral arms or elliptical blobs, under gravity's guidance combined with angular momentum and interactions. The reason many galaxies are roughly disc-shaped or ellipsoidal relates back to the same desire to redistribute mass where forces are balanced. You could see the whole universe as an ongoing exercise in compromise between different physical tendencies, but gravity is the baseline choreographer. On a personal level, thinking about gravity this way can be quietly reassuring. There's a kind of inevitability in the universe's preference for symmetry and calm. When life feels jagged and chaotic, it helps to remember that the universe itself spends its time smoothing things out. Not that gravity corrects personal messes, but the metaphor sticks. Persistent, small pulls, practice, choices, habits, reshape life far more than dramatic bursts. It's the steady insistence that changes the form. Visually, this section should feel like watching something both intimate and vast. Show a close-up of sand slipping through fingers, then dissolve to footage of a floating water drop, and then to wide shots of a glowing nebula curling inward. Let the soundtrack echo a steady, gentle pull, a low, calming drone that gradually rises as clumps form and light ignites. Use slow camera movements. Nothing here is rushed. Gravity's art is patient. Your pacing should be too. In the end, the sphere is more than a shape. It's gravity's signature, a reminder that when influences are equal and unconstrained, nature chooses balance. That quiet preference for evenness gives the cosmos an aesthetic not of chaos, but of calm symmetry. We live on one of those rounded outcomes, carried along by a force we rarely notice until we look closely. And when we do, we see that the cosmos isn't just a random scatter of bits. It's an artwork of pull and yield, patience and form. Think of building a sandcastle on the beach. At first you pick up damp grains and they cling together by surface tension in little lumpy piles. That's the same feeling, on an unimaginably bigger scale, that starts every planet. In a young star's disk, microscopic dust grains drift and collide. They stick not because gravity is strong yet, but because tiny forces, electrostatic charge, van der Waals attractions, make them cling like static charged hair. If you squint, those drifting grains are like a crowd at a concert, each one small and fragile, but together they can form something bigger. Those first clumps are awkward and irregular. They're like the rough outlines of things that might become important later, fragile aggregates that tumble through the gas, sometimes bouncing off one another, sometimes sticking for a moment and then breaking apart. Over time, with millions of collisions, some clumps grow into pebbles, then into boulders, then into kilometer-scale planetesimals. At this stage, the shape is a mess, a collection of loosely bound rubble made by chance. If you picked one up in your mind's hand, it would feel like holding a bag of rocks, jagged, irregular, proud of its protrusions. But mass has a way of changing the rules. Every extra bit of material adds to the object's gravity. Gravity is patient, weak at small scales, insistent when accumulated. When bodies reach a certain size, roughly a few hundred kilometers across, though it depends on composition, they cross a threshold. Their own gravity becomes strong enough to pull loose material down from high points and fill in the low spots. The peaks crumble, the valleys rise. It's as if the object takes a deep breath and relaxes, smoothing itself into a rounded shape. You can picture it like dough slowly losing the sharpness from a rough cut as it's pressed and smoothed by hands. This smoothing is called hydrostatic equilibrium. It sounds technical, but it's a simple idea. When an object's internal pressure and its gravity balance out, the body settles into a shape where all material feels the same gravitational tug. For a rotating body, the stable form is an oblate spheroid, a sphere slightly squashed at the poles. For a non-rotating body, it's a sphere. What matters is that the force of gravity overcomes the material strength that once held jagged edges in place. At that point, we stop thinking of the thing as merely an asteroid and start thinking of it as a world. Crossing that threshold is not a sudden, dramatic metamorphosis with fireworks. It's a quiet transformation, taking place over millions of years. Picture a mountain that looks immovable in your lifetime, but over geological time becomes a gentle slope. The same patient reworking happens on a planetesimal's surface. Impacts still scar it, and tectonics or cryovolcanism can reshape it further, but the overall curvature dominates. Once hydrostatic equilibrium is achieved, the body is forever smooth on the largest scales. That doesn't mean perfect, far from it. Mountains, rifts, and craters remain as tiny wrinkles on the rounded face, like freckles on a cheek. You can see the consequence of this threshold in our own backyard. Vesta and Ceres, both in the asteroid belt, tell different stories. Vesta, more rigid and slightly smaller, retains a lumpy, irregular basin from giant impacts. Ceres, with enough mass and possibly a softer, icy interior, is rounder. Pluto and Eris, farther out and made of ices and rock, are rounded worlds as well. Even small moons, if they're large enough, become spherical. Reaching that mass is the dividing line between being a big rock and being a planet, or a dwarf planet, depending on how many neighbors you have and how tidy your orbital house is. There's also a human side to this. When you look at a round planet, it's easy to feel that curve and imagine standing on its surface, watching the horizon tilt away. That curvature tells a story of accumulation and time, of dust grains that chose, in an unimaginably slow lottery, to become something more. Everything about a rounded world, the way air pools in lowlands, the way oceans must settle into basins, the way mountains stand as local anomalies, comes from that quiet rebalancing of forces. It's a reminder that scale matters. The same physics that makes a water droplet spherical after a fall also shapes planets when the numbers are enormous. Finally, remember that hydrostatic equilibrium is both an end and a beginning. Reaching roundness marks the birth of a world, but it also sets the stage for what comes next. Differentiation, where dense materials sink and lighter materials float. The retention or loss of an atmosphere, the possibility of internal heat and tectonics. The smoothness is the canvas, everything that defines a planet's character, geology, climate, potential for life, paints itself onto that curved surface. Dust becomes world, lumpy cluster becomes globe. And somewhere in that transformation, your imagination gets to stand on the edge and see the whole thing in motion. Gravity may be universal, but it isn't equally strong everywhere. And that's the first secret to why some space rocks look like angry potatoes instead of perfect marbles. Gravity's pull grows with mass. A planet has so much mass that everything inside it feels a steady squeeze toward the center. Rock and ice slowly slump and creep until the whole thing finds a balance, a sphere. Tiny things, they just don't have that luxury. Think about it this way. Take a snowball and a boulder. If you poke the snowball, it deforms and settles back. If you poke the boulder, nothing changes. That difference comes down to how easily the material yields. Rock, at the scale of a pebble or a small asteroid, is rigid. The self-gravity of a kilometer-wide rock is simply too weak to overcome its internal strength. The stone stays where its structure put it long ago, angles, ridges, chunks, even when millions of years pass. Now imagine holding one of these small bodies in your hand, not literally, of course, but picture it. Sharp edges, sudden cliffs, ragged boulders, stacked awkwardly. Every jut and dent is a scar. Most small asteroids and tiny moons are less like single, perfectly solid rocks, and more like conglomerates. Sometimes literally a pile of rocks loosely bound by the faint pull of gravity. Scientists call some of them rubble piles. After a violent collision shatters a parent body, the pieces can reassemble under their weak mutual attraction into an irregular lump with voids and seams. There's no internal pressure to smooth those seams away. Collisions are the chisels of the solar system. On Earth, we have weather, water, and tectonics to soften and erase impact scars over geologic time. Small airless worlds don't. A meteoroid smacking a tiny asteroid carves a sharp crater, sends off chunks, and leaves ridges and spallation, features that stay put because there's no atmosphere to redistribute material, and the gravity can't pull loose rocks into a smoother surface. Even micro-impacts over billions of years simply make the surface more jagged rather than more spherical. There's also a timescale trick. On big bodies, internal heat and pressure let rocks behave plastically over long times. Essentially, the rock flows, very slowly, to erase high spots and fill low spots. A mountain under a planet's own weight will slowly slouch. For small bodies, the internal pressures are tiny. The rocks don't flow. They fracture. So instead of a slow, even relaxation toward symmetry, you get sudden breaks and uneven rearrangements. Some of the best photographs from recent missions bring this to life. Spacecraft that have visited small asteroids find surfaces covered in boulders, seams, and sharp ridgelines. One famous asteroid looks like two lobes glued together, the telltale sign of a past collision and imperfect recombination. Others are roughly rounded but still pockmarked with giant rocks that look like someone tossed cobbles onto a beach and left them there. That roughness is meaningful. It tells a history of impacts, reassembly, and the limits of gravity. There's another way to picture the threshold between lumpy and round. Compare clay to a pile of gravel. If you press clay, it yields and becomes smooth because the forces between particles and the clay's own cohesion let it flow. A gravel pile will keep its jagged outline because the individual stones resist being forced into a smooth ball. Bigger bodies behave like the clay. Smaller ones are the gravel. Only once an object gets massive enough does its own weight overcome the stickiness of rock and ice and let the whole thing relax into a sphere. Material matters too. Icy moons can become spherical at smaller sizes than rocky ones because ice is softer under the same conditions. It flows at lower stresses. That's why some mid-sized moons of the outer planets look round even when they aren't huge. But for rocky asteroids and small, airless moons near the inner solar system, roundness is a high-pressure, high-mass privilege. There's a human angle to all this. We tend to think round things are finished or perfect, a polished marble, a smooth pebble. But in space, being lumpy isn't failure. It's biography. Those edges and ridges are signatures of collisions, tidal tugs, the gradual collection of debris, or a violent disassembly and reassembly after a catastrophic hit. If you could gently run your fingers across one, very gently, because those surfaces would be cold and strange, you'd be touching billions of years of chaotic interactions. Every uneven line is a sentence in its life story. And because their gravity is weak, small bodies can keep odd shapes for ages. They don't need to be stable in the sense of engineering. They only need enough cohesion and mutual gravity to avoid flying apart. That can result in bizarre silhouettes, elongated spindles, double-lobed peanuts, or cracked layered piles. In many ways, it's the opposite of what we'd expect from big, slow, patient planets. Small worlds wear their history on their sleeves. So, roundness isn't a universal goal that every object reaches. It's the end game of pressure and scale. Until a body grows heavy enough for its own weight to make the rocks flow and the peaks slump, it stays stubbornly itself, lumpy, scarred, and honest. And honestly, that's part of what makes those small worlds so fascinating. Their irregularity is a record. Their roughness is a diary. In every cliff and ridge, there's a memory of impact, escape, and survival. Until gravity becomes strong enough to iron it all out, each little lump carries its story in the lines and shadows you'd read if you had the patience to look. Think about the last time you spun something. A coin on a table, a pizza dough in the air, or even a fidget spinner. At first, it's just a solid shape. Then, as it spins, it changes. It flattens a bit, widens out, finds a new shape that fits the motion. That's exactly what happens to planets. They aren't perfect, mathematically flawless spheres sitting still in space. Instead, they are living compromises. Round, yes, but shaped by action. As a planet rotates, every bit of its mass wants to fly outward a little. That's centrifugal force at work, a tendency caused by spinning motion. Pull too hard one way, and the planet would tear itself apart. Pull too little, and it would collapse inward under its own gravity. So gravity and rotation negotiate. Gravity pulls everything toward the center. Rotation pushes material outward around the equator. The result? An oblate spheroid. Imagine a sphere gently squashed from top to bottom and slightly spread around the middle. It's a sphere with a quiet heartbeat of motion. Earth gives us a tidy example. From pole to pole, it's a little shorter than across the equator. The equator bulges by about 21 kilometers. That's 21,000 meters, compared to the pole-to-pole measurement. You can't spot that bulge by looking at a globe in your living room or from photos of Earth from space. It's too subtle for our eyes, but it's real and measurable. To put 21 kilometers in everyday terms, it's longer than the width of many countries' capital-to-capital distances, and more than twice the height of Mount Everest. Yet on a planet that's over 12,700 kilometers in diameter, that extra breadth becomes a quiet whisper of motion. There's something human about this. Most of us chase balance like it's stillness, a picture-perfect calm. But real balance is closer to the planet's compromise, movement held steady. Think about riding a bicycle. You're constantly shifting, micro-correcting with your body, and yet you appear balanced. The motion is the balance. That's what Earth teaches us too. Two invisible forces, gravity and rotation, don't fight to the death. They find a middle ground. The shape we live on is a roundness born from motion, not despite it. Different planets show this compromise to different degrees. Fast spinners like Jupiter and Saturn are noticeably more flattened at the poles and bulging at the equator because they rotate much faster than Earth. Their atmospheres ripple and shift in response, and the bulge becomes dramatic enough that spacecraft have to account for it when navigating close by. Even our own atmosphere, oceans, and the movement of tectonic plates subtly redistribute mass and nudge the shape over time. Nothing about a planet's roundness is static. It's an ongoing negotiation. Imagine the Earth as a slowly beating heart. With each rotation, we feel the consequences. Slight differences in gravitational pull, depending on where you are. Tiny changes in sea level, or milliseconds added or shaved from the length of a day over geological timescales. If you live near the equator, you're a tad farther from the center of the Earth than someone near the poles. Not enough to change your daily routine, but enough that scientists and engineers must account for it when they aim satellites, measure distances, or monitor climate and sea level. And that's powerful, because it asks us to reframe what perfection looks like. A perfect sphere might sound ideal on paper, but in nature, perfection often emerges through adaptation and balance under pressure. The planet's oblate form is elegant because it acknowledges forces instead of pretending they don't exist. It's a reminder that systems, whether celestial or personal, often perform best when they bend gently to the realities around them. So next time you spin a coin or balance on a bike, remember the Earth quietly doing the same. Its bulge is a small fact with a big lesson. Stability doesn't require freezing into one shape. It can be a living compromise, a graceful outcome of motion and restraint working together. Gravity and rotation reached an agreement long before we existed, and that agreement is the steady, slightly imperfect globe under our feet. If you look up tonight, every star you see is round. Take a moment. Lie back. Let your neck soften and pick a single point of light. At that tiny distance on the sky, it looks like a pinprick. But out there, each one is an immense, glowing ball of plasma, held together by gravity and shaped by a relentless internal tug-of-war. Think of a star like a cosmic pressure cooker. In the core, where temperatures and densities are extreme, hydrogen atoms crash together and fuse into helium. That fusion releases an enormous amount of energy as heat and radiation, and that energy wants to escape. It pushes outward, trying to make the star expand like steam inflating a kettle. Gravity, on the other hand, is the exact opposite force. It relentlessly pulls every particle inward, trying to collapse that hot, chaotic gas into a much smaller space. When these two forces equalize, when the outward push from fusion exactly balances the inward pull of gravity, the star settles into a stable, roughly spherical shape. That equilibrium is called hydrostatic equilibrium, and it's why stars are round. Why round? Because a sphere is the natural shape that lets pressure push equally in every direction against gravity. If any part of the star bulged a little, the local gravity would change and the pressure would adjust to smooth things out. Imagine pressing evenly on an orange from all sides. The fruit keeps its shape, except a star isn't skin and pulp. It's plasma, atoms stripped of their electrons, a soup of charged particles where electric and magnetic fields can dance. Yet, despite that complexity, the simplest geometric solution wins: symmetry. It helps to picture more familiar, smaller scale balances. Blow up a balloon and tie it off. The air inside presses out evenly, making a round shape. Drop a pebble into a calm pond and the ripples form concentric circles. Even when things are chaotic, equal pressures in all directions lead to symmetry. It's baked into physics. For stars, that symmetry is the difference between shining steadily for billions of years and doing something dramatic and short-lived. There are exceptions, or at least near exceptions, and they're interesting because they tell us more about the forces at work. Some stars spin so fast that centrifugal force, the pseudo-force you feel on a merry-go-round, starts to counteract gravity more strongly at the equator than the poles. Those stars bulge at the equator and flatten at the poles, becoming slightly oblate. Famous examples include Altair and Vega, which spin fast enough that telescopes can actually resolve their pancake-like shapes. The effect is visually striking when you realize that a star is not a fixed ball of fire, but a dynamic object with surface temperatures and radii that vary from pole to equator. Even then, though, stars maintain near-perfect symmetry. The Sun, for instance, would be only a few kilometers off from a perfect sphere if scaled to beach ball size. That tiny deviation isn't a flaw, it's a sign of balance. The sun's rotation is relatively sedate compared to those rapid spinners. The equator turns roughly once every 25 days. Though the surface doesn't rotate like a rigid body, the poles lag behind, and overall the sun remains remarkably spherical. Roundness, here, is not just balance, it's survival. Hydrostatic equilibrium is the star's state of quiet life. If fusion weakens in the core, gravity nudges the star to contract. Contraction raises central pressure and temperature, reigniting fusion or driving new fusion processes. If fusion becomes too intense, the star expands, cooling and changing the reactions in its depths. These adjustments keep stars alive on timescales that can span millions to trillions of years for different masses. When the balance finally breaks, when fuel runs out or core conditions change dramatically, the star can swell into a red giant, shed layers, or explode as a supernova. Those are the moments when roundness gives way to chaos. But during the long Middle Age, spherical symmetry is the maintenance plan that keeps the light on. Making this personal, think about times in your life when balance felt like survival. Maybe it was a period of steady work and simple routines that kept everything from spinning out, or a relationship that stayed healthy because pressure and support flowed both ways. Stars do that at an unimaginable scale. Their roundness is the physical record of constant adjustments, a visible form of resilience. When you look at a steady point of light tonight, you're seeing balance sustained over eons, the result of forces arguing and compromising long before humans ever named them. There's also a quiet beauty in the idea that shape can be a statement of health. A perfectly round star is not merely aesthetically pleasing. It's the result of microscopic collisions, nuclear reactions, and the smooth redistribution of energy. Even tiny irregularities can tell astronomers a lot. Differential rotation, magnetic activity, spots, or nearby companions tugging gravitationally. So when astronomers measure a star's deviations from sphericity, they're reading its biography. How fast it spins, how magnetically active it is, even whether it's part of a binary system. Finally, remember this. When you scan the sky, those pinpoints of light aren't just ornaments. They are weather systems and reactors and dynamos, each maintaining its spherical integrity through unfathomable internal violence. Roundness is what lets them keep shining long enough to seed planets, to forge the heavy elements that will one day become rocks and oceans and life. The next time you're under a clear sky, try to imagine the quiet negotiation at the core of every star, tiny particles colliding, nuclei fusing, gravity tugging, and a shape emerging that is both elegant and essential. That roundness is not an accident. It's the outcome of forces tough enough to shape the universe itself. Now shrink the scene down. Not mountains or moons, but a single suspended bead of water, the kind astronauts play with inside the International Space Station. Picture it, a perfectly round jewel-like drop floating in the cabin light, reflecting a tiny upside-down world. No drip, no trailing tail, just a flawless sphere. That image isn't magic, it's physics made visible. On Earth, we take the shape of a drop for granted and rarely notice why it looks the way it does. We're used to gravity dominating every puddle and raindrop. Outside air pushes, wind tugs, and gravity stretches a falling drop into a teardrop shape the moment it's big enough. But in microgravity, in that near-weightless environment aboard the ISS, all those usual forces are gone or tiny. What's left to sculpt the water is surface tension, and when surface tension rules, the result is strikingly simple: round. Surface tension is like a tiny local gravity acting only between molecules. Think of each molecule at the surface of a droplet as a person on the edge of a crowded dance floor. They're being pulled inward by all the people around them, trying to get snug in the center where they feel the most comfortable. The pull is electromagnetic in origin. Molecules attract one another, but the overall effect behaves like a force that wants to shrink the surface to the smallest area possible. For a given amount of water, the shape with the smallest surface area is a sphere. So the droplet becomes a sphere because that's the way to be most comfortable energetically. If you like little analogies, imagine wrapping a fixed volume of Play-Doh with the smallest amount of cling film. No matter how you try, the film will settle to embrace the clay in as compact a way as possible. In the microscopic world of molecules, surface tension is the cling film. It doesn't know about gravity or up and down, it only cares about minimizing the exposed area. On the ISS, you end up with an almost perfect mathematician sphere, smooth, symmetric, and calm. There's another neat truth here: the energy story. Everything in nature prefers less energy if it can get there without breaking a rule. For liquids, the relevant energy is surface energy, which increases with surface area. The molecules of the droplet arrange themselves to minimize that energy. That drive for lower energy is the same language physics uses whether you're talking about a droplet or a planet. It's the same verb, minimize, applied at wildly different scales. Bring gravity back into the picture and the narrative expands, but stays familiar. For planets and moons, gravity is the sculptor instead of surface tension. Every bit of mass pulls on every other bit, and the configuration that minimizes gravitational potential energy for a given mass and composition is, again, close to spherical. That's why planetary bodies above a certain size are round. Their self-gravity overcomes the rigidity of rock and metal and slowly pulls mountains and crust down toward a balanced spherical shape. Rotation complicates the story. A spinning planet bulges at the equator, but the baseline tendency toward roundness remains. So when I see a single water bead floating in a sunlit module, I can't help but feel some kinship with that distant, slow-motion work of planetary formation. It's the same principle playing out on a stage, with very different actors. The drop is small, immediate, human scale. The planet is vast, patient, and takes billions of years. But both are trying to get to rest. This also explains why we find round forms so aesthetically pleasing and reassuring. Our brains are tuned to spot simplicity and balance. A sphere signals a kind of settledness. No stress lines, no awkward edges, balanced forces. If you're holding a round stone or watching a bead of water float, there's an almost visceral sense of, that's finished, or that's right. Physically, that's because the object has reached a minimal energy configuration. Psychologically, our minds borrow that physics and translate it into a feeling of calm. There are fun experiments you can do at home that echo the microgravity scene, even if you can't get to orbit. Try putting small drops of water on a non-absorbent surface like a slick plastic or a freshly waxed car hood. Use a dropper, bring the droplets slowly together, and watch how they merge into larger, rounder drops. The edges smooth out. The beads coalesce to reduce total surface area. You'll notice the same instinctive motion. The drops move and settle until things look neat and compact. That's surface tension doing the work. It's less dramatic than a floating sphere, but it's the same principle at play. I remember the first time I saw footage from the ISS where an astronaut gently nudged a water bead with a paintbrush. The bead didn't spill or drip. It rolled, it rotated, it absorbed tiny splashes into itself, always returning to that pristine roundness. For a moment, physics felt like a choreography, molecules performing a careful, rehearsed dance. It made me think about how often we, as people, try to rearrange the surface of our lives, patching leaks, smoothing rough edges, to find a comfortable, simple shape. Energy, in its many guises, looks for rest. It's a humble tendency that we see from the laboratory bench to the outer solar system. So the next time you see a droplet on a leaf, on a window, or in a clip from space, take a moment to look closer. Notice how the light pools on its surface, how reflections curve around, how entirely small-scale forces can make something look so complete. The smallest spheres teach us a big lesson. Whether molecules are pulling inward or mountains are sinking outward, natural systems often seek the path to the simplest, smoothest configuration. Roundness isn't just pretty, it's physics catching its breath. Think of a galaxy as a city in motion. From far away, it might look like a fuzzy spiral or a soft ellipse, but up close, it's a bustling, twirling metropolis where every resident, every star, gas cloud, and dust lane is on the move. That motion is the sculptor. When a vast cloud of gas and stars carries even a whisper of rotation, it doesn't stay round forever. Conservation of angular momentum. The same rule that makes a spinning figure skater pull their arms in and spin faster flattens the system into a disk. That's why so many galaxies, including our own Milky Way, wear their beauty in sweeping spiral arms. You can picture it in more familiar terms. Imagine stirring cream into coffee. At first, the liquid is chaotic, but as you stir, patterns emerge, whirls and streaks that curve around a central point. Gas within a protogalaxy behaves similarly. As it collapses under gravity, the rotation spreads the material into a rotating disk. The result isn't a rigid pinwheel. It's more like a living, breathing dance floor where stars orbit the center in ordered paths, while new stars are born in the lanes where gas is densest. But spinning alone doesn't tell the whole story. Invisible to our eyes, dark matter forms a vast, spherical halo that cocoons galaxies. Think of it as the unseen scaffolding around which the visible parts build themselves. Without that halo, the graceful rotation we see wouldn't hold together the way it does. Observations of how stars and gas move, the so-called rotation curves, show us that outer stars are moving faster than we'd expect from the visible mass alone. That extra pull comes from dark matter, and its gravitational grip helps shape the galaxy's form. In other words, the elegant spiral we adore is a collaboration, visible matter tracing patterns within an invisible gravitational framework. Inside that structure, gravity still plays the consistent role of pulling toward the center. Even in a flattened disk, gravity is felt inward. Stars orbit because they're trying to fall in, but their sideways speed keeps them from doing so. This is why galaxies keep a rounded core a dense, spheroidal bulge where orbits are more chaotic and three-dimensional, while the disk stays flat and organized. If you could stand on a star for a moment, you'd find yourself following an almost circular path around the common center of mass, like cars cruising around a giant cosmic roundabout. The spiral arms themselves are especially interesting because they're not solid structures. They're more like traffic jams on the highway, regions where stars and gas slow down and pile up, triggered by a density wave sweeping through the disk. As gas clouds enter these denser regions, they get compressed, triggering bursts of star formation. That's why spiral arms glow with young, bright blue stars and the reddish glow of newborn stellar nurseries. Stars don't remain glued to the arm forever. They drift in and out, but the arm pattern endures because the underlying wave keeps moving through the disk. Galactic collisions and interactions also sculpt shape. Two spiral galaxies that brush past each other can fling out long tidal tails, or even merge into a more rounded elliptical galaxy. These violent encounters scramble orderly rotation and send stars into more random orbits, favoring a smoother, sphere-like distribution. Yet even in these chaotic reorganizations, gravity insists on centering mass, creating a rounded, compact heart to the new system. If you zoom out even further, you start to see that the universe itself has a taste for curves. The cosmic web, the large-scale pattern of galaxies and clusters, isn't arranged in sharp angles and straight lines. It forms filaments and sheets that arc and bend under their mutual gravity, connecting dense nodes like a network of gently curving bridges. Voids between them are smooth and rounded, not boxy. From the scale of a single star system to the tapestry of the entire cosmos, gravity tends to smooth and round things out. There's something almost comforting about that. Human life is full of jagged edges, deadlines, unexpected turns, broken plans. Yet when you look up and imagine galaxies spinning, vast, patient structures turning under the same laws that govern a spinning top, it's a reminder that motion, even messy motion, can give rise to order. Even chaos, when seen from a distance, folds into graceful arcs. So the next time you picture the Milky Way as a painted swirl across the night, remember what's holding that image together: rotation sculpting the disk, dark matter's invisible hands providing structure, and gravity constantly pulling everything inward. Those sweeping arms aren't decorative flourishes. They are the fingerprints of motion and mass, curving elegantly because that's the universe's favored choreography. Think of a soap bubble. When you blow one, all the messy ripples and eddies of air and soap film settle themselves into a single, perfect round shape. Black holes do something like that on a cosmic scale. When a massive star runs out of fuel and gravity wins, everything that made the star interesting, its layers, its magnetic fields, the chaotic storms of plasma, is dragged inward. Matter, radiation, and even space-time itself are pulled down until they pass an invisible boundary, the event horizon. From the outside, everything beyond that boundary is hidden, and what's left is the simplest possible shape gravity can make. That boundary, the event horizon, is what we mean when we say black holes are the roundest objects of all. The horizon forms a perfect sphere around the singularity at the center. You can try to picture the singularity as a point of infinite density, a concept that gets tricky in the math. But the horizon is the part we can talk about more confidently. A smooth, spherical surface in space-time that separates the inside from the rest of the universe. cross it, and escape is impossible. Remain outside, and you can only infer what's within by the way the hole tugs on nearby matter and light. What makes this so striking, and why it feels almost personal, is the way black holes erase detail. Imagine taking a photograph of a person and then blurring it until only a single basic silhouette remains. That's what gravity does here. No matter how complicated the collapsing star was, how lumpy, magnetized, or rotating, the event horizon that forms is remarkably featureless. In physics, this becomes a profound statement. The external appearance of a black hole can be entirely described by just a few numbers, like its mass and spin. The universe has distilled everything down to a handful of properties and a perfect shape. You might wonder, what about spinning black holes, or two black holes smashing together? Surely that would wrinkle the horizon. In fact, even when black holes rotate, and many do, they remain elegantly symmetric. Their horizons are as smooth and round as the rules of general relativity allow. When two black holes merge, the process can be wildly violent. Tides of space-time sloshing, jets of energy, and a final ring of gravitational waves. Yet after the merger, the newly formed black hole settles, like a struck bell returning to silence. The distortions radiate away as gravitational waves, and the horizon relaxes into that same clean, spherical form. It's a cosmic example of taking the loudest possible action and leaving behind utter simplicity. There's a human comfort in this idea. We live in a world of cluttered detail, messy desks, complicated relationships, lists that never end. The black hole's simplicity is almost an extreme kind of calm. When everything else fails, when heat, light, and structure are swallowed, what remains is geometry. That final state is pure curvature, space bent into a shape so simple that it needs no decoration. It's gravity's final statement, and it reads like minimalism in the language of the cosmos. This doesn't mean black holes are physically uneventful. The region just outside the horizon can be a circus of high-energy physics, matter spiraling in, magnetic fields whipping, orbits precessing in strange ways. But all that activity never leaves an imprint on the horizon itself once the black hole relaxes. If you stand metaphorically at a safe distance and watch, the horizon is like a perfectly calm lake whose surface hides a tremendous depth below. The calmness is the power of gravity at work, sufficient to smooth out any feature, to average away chaos into symmetry. A useful mental picture is to imagine pebbles in a stream. The river's current polishes them over time, removing rough edges until they become smooth, rounded stones. Gravity does something analogous, but vastly more absolute. Instead of water wearing away rock, it's the dynamics of space-time, the way gravitational energy radiates out, that polishes the hole's external form. In the end, nothing but pure curvature remains to be measured. There's also a poetic hush that comes with this concept. The word black in black hole tells part of the story. Not only is light unable to escape, but our usual ways of describing things, pictures, direct observations, are cut off. We can detect their presence and listen for their mergers in gravitational waves. but the interior is silent to electromagnetic probes. That silence, combined with the horizon's roundness, gives black holes an almost meditative character. They are endpoints in astrophysical processes where complexity collapses into a quiet, geometric truth. Finally, this idea leads to deep questions that tug at both science and curiosity. If externally, a black hole is defined by only a few quantities and a perfect shape, what does that say about information and identity in the universe? Physicists still debate how or whether the details of the matter that fell in are encoded somehow. But whatever the answer, the horizon's roundness stands as an elegant anchor, a clean, geometric result of nature's most extreme forces. So when you picture the most perfectly round object in the universe, don't think of a manufactured sphere or a polished marble. Think instead of the result of collapse and loss, of a boundary that says, this far and no further. It's not beauty in the ornamental sense. It's beauty as final form, gravity speaking in its most economical, uncompromising voice. Think of a drop of water on a table. If you nudge it, it wiggles, then settles back into that perfect little dome. That dome isn't arbitrary or decorative. It's the most economical shape the drop can make while holding all that water together. Gravity plays the same game on a much larger scale. At its heart, roundness is an answer to a simple problem. You've got a lump of stuff, and there's a pull acting the same from every direction. What shape resists that pull with the least fuss? Mathematicians and physicists give the same answer: a sphere. In plain language, for any given amount of stuff, volume, a sphere has the smallest possible surface area. Less surface means less edge to stress, less area for forces to fight over, and that translates into less energy locked up in the system. Nature, being stingy with energy, prefers that. You can see the same principle in tiny, everyday scenes. Blow a soap bubble with a ring. The soap film straight away becomes a sphere because surface tension is minimizing the area of the film while enclosing a fixed volume of air. Watch water bead up on a waxed car or on a leaf. The droplets minimize their contact area, forming near spheres. Those are surface tension examples, but gravity acts in a comparable way for big things. It's the same drive toward balance, just with a different force dominating the bookkeeping. When an object gets massive enough that its own gravity becomes the strongest influence on its internal structure, the material inside flows, very slowly if it's rock or metal, quickly if it's gas, until the inward pull is the same from every direction. That state, hydrostatic equilibrium, is essentially a situation where pressure balances gravity. The only shape where the gravitational pull looks identical, no matter which direction you measure it, is a sphere. So planets and stars, which are held together by self-gravity, naturally settle into spheroids. The math behind this is elegant. It's the isoperimetric principle. In 2 dimensions, the circle encloses the maximum area for a fixed perimeter. In 3 dimensions, the sphere encloses the maximum volume for a fixed surface area. Flip that statement, and you get the form we use here. For a fixed volume, the sphere has the least surface area. That's not just a cute geometric fact. It's a rule that minimizes energy. A system with less exposed surface or less internal stress consumes less energy maintaining that stress. So evolution, physical evolution, pushes systems toward that state. It helps to imagine the inside of a planet like a layered cake, but with layers arranged by pressure, not frosting. At every point inside, the material feels the collective tug of everything else. Deeper down, pressure is higher because it supports more weight. The configuration where these pressures and gravitational pulls balance everywhere is the one with spherical symmetry. If you tried to make a planet shaped like a potato, pressures at different points wouldn't match. Material would slowly flow toward a state of lower energy, nudging toward roundness until the imbalance is gone. This is why we say gravity is a sculptor that prefers symmetry. There are, of course, caveats that keep things interesting. Small bodies, like many asteroids, don't become spherical because their self-gravity is too weak compared to the rigidity of rock. Material strength can resist the pull, letting them keep odd, lumpy shapes. But once the mass is large enough that gravity overwhelms internal rigidity, roughly a few hundred kilometers across for rocky bodies, less for icy ones, the object succumbs and rounds out. Even then, perfect roundness is rare. Rotation makes planets bulge at the equator. Tidal forces stretch moons into ellipsoids, and local variations in composition and temperature can create bumps and trenches. Still, the dominant tendency is toward a sphere. I like to think of it like people seeking comfort. If you want to relax, you don't sit on a bed of nails. You lie in a hammock that cradles you evenly. Nature, through gravity, is setting up a hammock for matter. Every bit of it finds the easiest place to be. If it's allowed to move, it will. Energy flows downhill in the abstract sense. Systems shed irregularities and stress until they reach equilibrium. And in 2 dimensions, equilibrium looks circular. In 3 dimensions, it looks spherical. That's why so many things, from the tiniest droplets you can coax on a fingertip to the largest gas giants in the sky, end up looking like they were drawn with a compass. There's also a poetic angle. Symmetry is the quiet end of struggle. When all forces are balanced, there are no preferred directions left. The object becomes indifferent to orientation. That indifference reads to our eyes as beauty and to our physics as minimal energy. Gravity isn't malicious or petty. It's efficient. It erases drama by evening things out, and that gentle leveling often results in the simplest, smoothest shapes imaginable. So next time you look at a droplet, a planetarium model, or even a perfectly round marble, remember that roundness is an outcome, not an accident. It's the signature of forces that care only about balance, economy, and the path of least resistance. Gravity chooses roundness because roundness is the shape of peace for matter under equal pull from all sides. Yet gravity's favoritism for roundness is only part of the story. If you stare long enough at the sky, what really grabs you aren't pristine spheres, so much as the moments when that perfect pull is interrupted. When something else nudges, scours, or stirs. Those interruptions are where the universe starts to feel alive. Think about Saturn's rings. From a distance, they read as a flawless, flat disk, the poster child of circular perfection. But get closer in your mind's eye. They're not a solid sheet. They're trillions of icy particles, each following its own orbit, colliding gently, forming wakes and ripples. The rings are flat because motion and gravity sort the particles into a plane, but inside that plane there's chaos. Tiny clumps, gravitational shepherds, waves that betray a dynamic, ongoing story. That thinness is its own kind of imperfection, a fragile balance between order and motion. Mountains rising above planets feel like a contradiction to gravity's thesis. We talk about planets being round, but look at Earth. Ridges and peaks that keep their shape for millions of years. On bodies with less active geology, like the Moon or Mercury, impact craters leave mountains and scarred plateaus that never heal. These features are records, not mistakes. Each ridge, each jagged peak, is a page in a planet's history. Imagine an old photograph where the grain and crease make the portrait more honest. Planetary mountains are the same. They break the ideal and tell us what happened. Then there are the asteroids and small moons, lumpy, misshapen rocks tumbling through space. Their inability to become spherical is not failure, but an honest consequence of scale. When gravity is too weak to round them out, their surfaces preserve the violence of formation. Pockmarks from collisions, boulders perched awkwardly, surfaces peppered with irregularities. I always find them the most relatable. They remind me of the way a childhood toy, battered and scarred, holds more personality than something brand new and perfect. Galaxies, meanwhile, write their own rules. We might picture them as elegant disks, but many twist themselves into splendid bars and spirals. That bar across a galaxy's core is not cosmetic. It funnels stars and gas, fuels new star formation, and reshapes the galaxy over eons. Spiral arms are waves of density and motion, not static structures. They're stamped into the stellar population by gravity and rotation, and then left to evolve. A galaxy's asymmetry is a fingerprint of its interactions. A near miss with another galaxy, the tug of a satellite, the long memory of past collisions. When you watch these enormous systems, you're watching slow motion choreography, where balance trembles into beauty. What does this all have in common? Motion, heat, magnetism, and time. These are the forces that complicate gravity's neat solution. Heat drives convection, which sculpts clouds, drives winds, carves canyons, and makes Jupiter's bands and storms dance. Magnetism shapes plasma, lights up auroras, and corrals charged particles into belts and filaments. Time lets small imbalances amplify, lets scars persist, lets textures form from tiny fluctuations. Even rotation, a simple everyday twist, flattens and elongates, giving us oblate planets, rings, and barred galaxies. There's a human truth hidden in these cosmic wrinkles. We tend to chase perfection, smooth designs, flawless surfaces, seamless symmetry. But I find myself drawn to the same flaws that make a pebble interesting, a face memorable, or a song moving. The crack, the accent, the unexpected harmony. The universe is like that too. If everything were perfectly spherical, perfectly smooth, the cosmos would be elegant but mute. Those deviations, a ridge that refuses to level, a ring particle that won't fall in line, a spiral arm that sings slightly out of tune, are the notes that give the symphony its character. So as you listen to the symmetry of gravity's work, don't forget to lean in where it trembles. Beauty often lives in those moments where a sphere becomes a swirl, where a planet keeps a stubborn ridge just for texture, where a galaxy adopts a bar and a set of arms and tells you about its past encounters. It's in the imperfections that the universe writes its stories, And it's those stories that keep us looking up. Picture the universe like a room with no corners, a place where every edge has been softened until there's nowhere to jab or cut yourself on. That softness isn't just an aesthetic choice. It's physics humming a lullaby. When you imagine stepping outside of everything and looking back, the first thing that settles in is not the jaggedness of things, but the way they curve into one another, as if the whole scene had been modeled on a single, patient hand. That hand is gravity, and its handwriting is round. Think about a droplet forming on the tip of a leaf. Surface tension gathers it, pulls it inward, and the result is a perfect, trembling sphere. The droplet doesn't hurry to be round. It simply follows the rules of the forces acting on it, and roundness emerges as the peaceful solution. Now slide your gaze up the scale. The same tendency shows up in the way planets settle into orbits, the way galaxies swirl into arms, the way space-time itself responds to mass. Different actors, same choreography. It's almost as if the universe has a favorite shape for resolving tension. There's a comfort in that. Not because everything is tidy. The cosmos is full of explosions, collisions, and chaos. But because, over time, those disturbances are smoothed, energy dissipates, angular momentum redistributes, sharp gradients mellow into gradients of gentleness. Nature doesn't erase change, it translates it into curves. A comet's tail will be dramatic and fierce for a while, then long, graceful, and arcing. A mountain range will be jagged when young and softened by weather and time. Even the most dramatic events settle into rhythms that hum with the same rounded note. You, right now, are part of that process. Your life has edges, abrupt decisions, painful losses, sudden joys. But the world around you is gently conspiring to round those edges. Think of a scar. At first it's raw and angry. Months later, it's a pale arc that catches the light differently. That arc doesn't mean the memory is gone. The history is still there. But the shape has changed. That's the secret shape of peace. Not the absence of history or hurt, but the changing geometry of how those things sit with you. A curve holds the story differently than a spike does. What does that feel like in your body? If you're tense, your jaw clenches, your shoulders box forward, your breath stays shallow. Curving is literally easier to breathe into. Tilt your chest open in a gentle arc. Let the ribs widen like a horizon line, and your breath will find a fuller story. When you soften the angles in your life, you invite rest. Try this. When a stressful thought arrives, imagine it as a sharp pebble dropped into a pond. Watch the ripples spread and become circular. The energy of that pebble doesn't vanish, but the pond's response is circular, even, and eventually still. You're not denying the pebble, you're watching how the pond chooses to resolve it. Roundness also speaks of connection. A circle has no preferred point, no beginning or end that matters more than another. And that's a humbling idea. We often act like our personal dramas are the central spike that everyone else orbits. But from the geometry of the cosmos, every particle, every person, is part of the same curvature. The galaxy doesn't favor one star over another. The gravitational field simply reaches. That sense of shared belonging shifts perspective. If the universe is, in some poetic sense, biased toward connection and balance, then your own impulses toward mending, toward patience, are echoes of a much larger rhythm. This isn't merely poetic consolation, it's practical. When you notice someone pushing against you, a friend, a partner, a colleague, remember the curve. Resist the urge to respond with an equal and opposite spike. Instead, model the physics of the world. Soften, redirect, release. In everyday terms, it looks like asking a question instead of firing back, taking a pause before answering an accusation, or offering a small act of care when anger would escalate. These are the ways you practice leaning into a shape that preserves relationships rather than piercing them. The universe's pace matters too. It's tempting to chase immediacy, to want answers and changes now, as if balance were a sprint. But curvature is the signature of time. To bend, things need time to yield. A river carves a canyon not by force, but by patient repetition. If you want to build peace in your life, you have to be willing to be gradual. Small, consistent acts compound. A steady breath today is a calmer nervous system next week. A conversation held with curiosity now saves many sharp confrontations later. And then there's the wonder, the quiet joy of being a small part of a grand, smoothing movement. There's relief in recognizing that you're not the ultimate architect of how everything folds into shape. You are a note in a longer melody. That doesn't make you insignificant. It offers a kind of permission to rest, to fail, to change shape without shame. The universe's curve does not judge, it enfolds. So when life feels raw or rushed, remember the secret shape. Look for the spheres and spirals around you. A child's bubble, the way a cat curls on a sunlit chair, the slow spin of the Milky Way on long exposure images. Let those shapes be a small education in patience and belonging. Practice softening the angles you can control, your posture, your words, the tiny routines that guide your days. Over time, you'll notice a subtle rearrangement of the landscape inside you. Pain will keep its history, but it will sit differently. Joy will be less brittle, more able to spread. We don't have to fabricate peace out of nothing. The universe is already offering a model. Roundness as resolution, connection as the default, time as the agent of smoothing. When you let that logic into your life, you begin to move with the same gentle gravity that shapes stars and droplets alike. In that movement, peace becomes less an abstract goal and more the natural consequence of living with a little more curve. Look up for a moment, not to judge the night, but to notice how everything up there is round. The moon wears a calm face. Planets hang like coins on a vast, dark table. Even the distant pinpricks of stars are soft circles when you stop trying to name them. This is not just picture-making. It's a quiet law the universe follows. Things, given time and space, smooth into curves. Corners ease, tensions relax, systems settle. Breathe in slowly. Feel that same rule working inside you. Your ribcage opens into a gentle arc. Your exhale rounds the shape of your shoulders down into the bed. Heartbeats, when measured in the small hours, are not sharp commands, but soft thumps, guided by the same pull toward balance. Think of your breath, as a tiny orbit. In, pause, out. A miniature planet tracing the same patient pattern as the world above. You don't need to fix everything before sleep. The physics that shaped mountains and oceans doesn't rush. It nudges. Let that thought be permission. The things you couldn't finish today are like rough stones at a creek's edge. Given time and a little current, they will be worn smooth. Tonight, the current is the slow metronome of your breathing. Match it, and let the edges dissolve. If a worry starts to poke at you, a corner of an unfinished conversation, a deadline, a memory, picture it softened by time. Watch it as if from outside yourself, an angular thought that grows rounder with each breath you give. No need to force the change. You are not reshaping your life in one night. You are allowing the same long, steady rule that shaped the sky to do its understated work inside you. The universe has been rounding things for billions of years. It can round a single raw thought tonight. Think about the rhythm of things you love, the circle of friends you return to, the daily loop of tea and newspaper, the arc of seasons. They are all examples of return and ease. Sleep is simply another arc in that same pattern. Descent into rest and the quiet return of morning. When you accept that sleep is a natural curve, it stops feeling like failure and becomes a necessary part of the geometry of your life. Now, very slowly, breathe in for 4 counts. Hold for 2. Exhale for 6. With every exhale, imagine one of those sky circles gently descending, not as a weight, but as a calm. Let it land across your forehead, your jaw, your shoulders. Let it sit there and make things rounder. Less rigid jaw, less clenched hand, less sharp thought. If your mind wanders, guide it back without judgment to the image of circles. Circles are not perfect, but their imperfection is kind. They give you room. Remember a small, ordinary moment of comfort, a warm cup cupped in both hands, a laugh with someone who knows you, a favorite song's final note fading. Hold that for a beat. Notice how your breath responds, how your body eases. This is the same easing the cosmos practices. Tonight, it's practicing it with you. You might notice tension habitually living in certain places, the neck, between the shoulder blades, the space behind your eyes. Direct a gentle breath to each of those places, as if you were tracing a round palm over them. Breathe in comfort. Breathe out release. Let each exhale be the tiny erosion that turns a sharp ridge into a gentle slope. There is no schedule for how long this rounding takes. Sometimes it is overnight. Sometimes it takes the length of a week, a year, a lifetime. The important thing is to trust the process. The laws that shaped worlds are patient. They operate beyond urgency. You can borrow that patience now. Let the urgency of worry loosen its grip. Let expectation fall away. Slow becomes enough. As your breathing finds that even, circular pace, allow the last images of your day to blur at the edges like ink in water. Your thoughts will roll toward calm the way a pebble rolls to the center of a bowl. Tonight, the universe continues its long, gentle work. It isn't forcing anything. It is merely making room. So rest into the roundness. Feel the night sky's quiet rule move through you, softening, leveling, easing you towards sleep. Let your thoughts become spheres that can roll, not sharp angles that catch. The world has been rounding itself for eons. Tonight it rounds your thoughts too, gently and endlessly, until you fall asleep.